All right, so what we're going to do now is begin with chapter 4.2.1, and that is titled Electric Charge. So in this chapter, we're going to talk about what electric charges are, right? How do we get them? Uh, Different types, so to speak, and the materials, right? And so to start off, I'm going to share two videos to sort of demonstrate charge. In this case, it's not current as we know it, but it does represent, charge, and then we talk about it and explain it. So let me just put that up on screen. All right, can you see that?
Yes.
Yes.
Okay, so just see what this person's doing, right? And we'll talk about it. Did you want to see it again?
Yeah.
It is a short.
No.
Right, so he rubs that material over the plastic thing, and then the plastic rod. Plastic is like we're using the term generally, and so you can see if he throws it in the air, and because of the rod, those hair like plastic things are floating.
So what causes that?
Yes, we will talk about that. Here's another short which is something we can relate to, especially in the winter.
কই তো
Did you notice what happened?
No.
Okay, so this man, what he's doing, he's taking like a shawl and he's rubbing it over the kid's head. And then, right now, nothing happens then. But the other kid, when he brings his finger close to the one sitting on the chair, there's like you can barely hear like a very small spark. And so,
Oh, you can feel a little current, right?
yes. And so, especially during the winters, it's sometimes touch something, especially if it is a conductor, even if it's not metallic, or you have your blanket on and you're removing a blanket or your jacket, and if it's dark, you can even see sparks happening when you're removing it, or you shake someone's hand and you sort of feel like a spark or a current. Has that ever happened to you?
Yeah.
Karan?
Yes.
Yeah, exactly. So that's what's happening over here in the video. So I'll just like play that again.
কই তো
So that was us removing our jacket or blanket or whatever, and then this happens. Right?
Yeah.
Okay. Now, why that happens is what we'll talk about. So, whiteboard. And why that happens is because of charges. A charge, right? A charge is something that produces current. Right? And the flow of charge is electricity. Right? So basically what we are feeling is like a very minor electric shock, so to speak, in that case.
Yeah.
Right? And so charges are of two types. There's a positive charge and negative charge. And as we talked about with magnets, positive charges attract like likes. Let's just go with this: likes repel and opposites attract. Right? And so in this case, right, if you have two positive charges, they will sorry, wrong arrow, repel. And that's what we saw happening in the first video. So when that person rubbed that cotton wool type of material on both those plastics, they both developed the same kind of charge. And so, right, when he threw that thread like plastic in the air and he kept the rod underneath it, the rod was perhaps positively charged, and those thread like things were also positively charged. And the reason why they were floating with the rod was underneath, because they were repelling each other. Okay. In the second video, what you saw is a man rub, that shawl over the kid's head. And so the thing is that the human body is a conductor, right? It allows charge to flow. And so that's why sometimes when you are dealing with electronic appliances or something, you can feel current, right? And that is because current can flow through the human body. So what happened is that that child's body developed a charge, let's say positive charge, right? And the other kid comes in, and because it's a conductor, now in this case, the first video you saw, they were both plastics, and plastics are not exactly conductors, right? Now, why they developed a charge, we'll talk about that. But in the case of the human body, right, it is a conductor. So let's say the kid who had the blanket rubbed over his head, he developed a positive charge. The other kid comes in, right, and the charge flowed, right? And so there was a spark meaning current, right? And so he felt like a very, very, very minor, right, isolated electric shock. Make sense? Sort of? Just to.
Yeah.
Now, going further into this, by the way, this is known as, we know what electricity is. This phenomenon that we saw in the videos is known as static electricity. Again, why is it called static? We'll briefly come to that. But the main principle of charges is true for, right, all. Likes repel, opposites attract, right? And so in the case of opposites attract, the charge flows. Okay. So to understand this, we need an understanding of the atom. And since we're doing chemistry as well, we know that atoms of substances, of materials, right, they have a nucleus which contains the protons, which are positively charged, and neutrons, which are neutral. And then surrounding the nucleus are the electrons, right, which are negatively charged. We know this, right? Now, on a whole, you take any atom and the number of protons equals to the number of electrons. And so the charge of an atom is 0 on its own. Now, just like a short reference, right, this is the basis of ionic bonding, that atoms lose or gain electrons, and so they develop a charge, and those are called ions, right? But ions are not what we're talking about right now. So two things can happen, right? You have materials that are called conductors, right? Conductors of electricity. And so basically what these guys have is they have electrons that can flow, and obvious examples of that are metals. And so metals have one or more electrons that in a metal, as we've talked about in metallic bonding, right, it's moving throughout, and so it can move about. So anywhere between 1, 2, 3, 4, even more depending on transition metals, right? So at least one, if not more. And so metals,
I have a question.
yeah,
Like diamonds also have like electrons floating, but
not
they don't
diamond,
conduct electricity.
not diamond does not.
Or graphite.
Yeah, so graphite can conduct electricity. Graphite can, and in fact it is used. If you recall, when we did electrolysis, sometimes or many times inert graphite electrodes are used in electrolysis. Remember?
Yeah.
Yeah, so graphite does conduct electricity. Okay. So metals have those electrons to move about. Right, they're called delocalized electrons, so they're moving about the entire metallic, between all the metallic atoms. And then you have insulators, right? And they do not have any electrons that are delocalized. Again, so metals, carbon as well, right? And so when they don't have delocalized electrons, what happens is, if you have an insulator, like the plastic or rubber wrapping around electric wires, that is to insulate the current that is passing through the copper, that is the actual wire, right? So this is the wire, and we know that, right, there is like a plastic rubber coating over it. We've seen wires, right? Like
Yeah.
you take your mobile charger or your laptop charger or any other wire, the wire that's connecting your mouse to your laptop or anything. So there's metal inside, and it's covered with plastic, and so plastic is insulator. Why? Because it does not allow charge to flow, right? And so it insulates. It stops the electricity, right? And that's what protects us. Even holding the wire, we're not feeling the electricity, even though electricity is flowing inside, if it is turned on, if it's connected. Now, in the case of the first video, at least, right, what happened was, like, metals can lose electrons on their own, right? So that's a separate thing. And like Haram mentioned, carbon, right? So in graphite, it can conduct electricity because it has an electron available. But in the case of the first video, when that person rubbed both those thread like plastic and the plastic rod with that cloth, what happened is, because of friction, remember friction,
Yeah.
right? Because of friction due to the rubbing, right, some electrons from those materials were lost. They were removed just because of physical friction, right? Because I'm rubbing the cloth over it, it's like sort of scraping the electrons off. And what happens when you lose electrons? The atom becomes positively charged, right? And so he did that with both materials, and then both materials became positively charged, and then they started repelling each other. So, right, and obviously this happens like for a short while. It doesn't, right? So somehow they sort of like, when if charge flows or something happens, right, it sort of neutralizes and loses that, right? So it regains the electron later on, right? Static electricity does not last for a very long time. So the Sobi, does that answer your question how that was happening?
Yeah.
Okay.
Yeah.
All right. Any questions so far?
No.
Now, honestly speaking, the way they've presented information in this chapter, I don't like it very much. It sort of feels like it's like just a random presentation of like, oh, here you go. This.
Yeah.
Right? So electrons, right, they in conductors they're able to move freely, right? Whereas in insulators, you don't have any electrons, right, do not or cannot move freely. Okay. Now we have materials that are good conductors, such as metals and carbon. We have metals that are good insulators, such as plastics, right? Polythene and cellulose acetate, nylon, perspex. Uh, and then we've got materials. So we've got good conductors. We've got good insulators, right? These are nylon, perspex, right? So different forms of plastic. And then you have poor insulators, which means they don't do as good a job in stopping the flow, which means that they are also poor conductors. So they allow some of that charge to flow. And examples of that are wood, right? Paper, cotton, and the human body. Okay, and also the earth, like the earth as in the ground, the earth that we walk on.
Okay.
So they kind of stop it, but kind of let it go through. So 50-50, you could say, right? So they're not good at doing either of those jobs. And then you got water, right? So water will conduct electricity if it has ions in it. Pure water that is just H2O, right? So pure water that is just H2O with nothing dissolved in it will not conduct electricity. But normally you have a lot of dissolved minerals and ions in it, like obviously sodium and chlorine and other stuff. And when you've got these guys, water will conduct. And so salt water is a very good conductor of electricity. Even tap water will conduct it because you got lots of stuff mixed in there, right? And because of that, for example, if you have water on something like glass, now glass itself is not a conductor, but if there's water on the glass, it will conduct electricity. What's actually conducting the electricity is the water. Okay, it's not the glass itself. Does this make sense?
Yes.
Yes.
Okay. And finally for today, I believe electric fields. Right, so we talked about magnetic fields recently, and so this should not be difficult to understand. Right, so an electric field is an area where right, an electric charge experiences a force. So it is the region, or what was the word you used, Sobia, for magnetic field? It is the,
Sorry?
you used the word for magnetic field, right?
Range?
Range. Yeah. So region where or in which an electric charge experiences a force. Right, and so what kind of force? So right, just like for magnets we had the convention that the field goes from north to south. For charge we have the convention, like for electric field, sorry, not charge, we have the convention that the field goes from positive to negative. Okay, so right, if you have, for example, a positive charge coming in, right, and it's going through here, it will be deflected because it will be repelled by the positive side, it will be attracted by the negative, right? But if you have a negative charge coming in, it will go the other way, right? And so within the electric field, right, and a charge will experience that push or pull. So what is the force, right? We say it's experiencing a force. Remember the definition of force. A force is a push or a pull, right? Now, electric force or magnetic force or gravitational force, as we mentioned way back in unit 1, these are non-contact forces, right? They don't need to touch for the effect, right? Whereas pushing and pulling physically, like I'm pushing a crate, or I'm pulling or pushing a trolley at the supermarket, or I'm pulling something, that are those are contact forces. Friction, air resistance, all of those, drag, those are all contact forces, right? Because they need to touch physically. Well, I shouldn't say physically interact, they need to touch to have an effect. Gravity, magnetism, electric fields, they don't need to touch. Clear?
Yes.
Yes.
Okay. Now, just like we mentioned, right? The convention is for the magnets we talked that we said that we set the north pole as a standard, and we talked about that. In electric fields, the positive terminal is the standard, and so when we are like I do the lines from the positive and negative, so the direction of an electric field right is the direction of the force of the force on a positive charge at a point, right? So we look at this guy, we put him in the right terminal from where, or the part from where it is being repelled. So likes repel, so that's positive. The one it's being attracted to, that's negative, right? And so the direction is from positive to negative. And okay, uh, for a sphere that is conducting, if you have something that's round, Let me, in fact, give myself some space over here. Right? What does the electric field look like? If this guy is positively charged, because we know it goes from positive to negative, the electric field will be moving away, so it's moving out. And if you have a point charge, so that too, right, the field will be away from the positive charge. Whereas if you have a negative charge, right, this is how you will draw it. In fact, let me draw the arrows towards the negative charge. Okay.
Yeah.
Can you explain that again?
Okay, so what did you say? Right, the electric field goes from positive to negative. That's the direction of the field. So if you have something that is only positively charged, what will its field look like? Its field will be going out.
Well,
Whereas if you have something negatively charged, right, because charge goes from positive to negative, but this is only negatively charged, right? Just negatively charged. The field around it will be attractive, will be pointing
yes.
towards it. Okay. Okay.
So negative will attract while the positive will push it away.
Yes, and that is because we've put the standard as a, with reference to a positive charge. What will happen to a positive charge? So positive charge will be repelled by the positive field and attracted to the negative field.
Okay.
Now, lastly, we talked about static electricity, right? Now, why is it called static? Why? Because in metals, you have electrons that are free to move about. We talked about that. In static electricity is something you experience with non-conductors. So on their own, we talk about plastics. Plastics are non-conductors. In fact, they're insulators. So what happens is, due to friction, right, when they lose electrons, they only lose electrons at a certain point, right? Because of that, it doesn't begin to flow. It doesn't move forward, right? And so it's stationary in place. So not in place. And something that does not move, it stays in place, is called static. And that is why that kind of, current or charge that is developed, like we saw in the video I talked about earlier, that is called static electricity. So even though some electrons were knocked off due to friction, due to rubbing, the charge is not flowing through the material. It's just there. It's just sitting there in its place. Okay.
Yes.
Okay. Anything that I missed? Oh, by the way, all fields, like a magnetic field and electric field, right? They are vectors. And with vectors, what do they have? They have magnitude. So how strong they are or weak they are, and direction, which you've seen. Fields have direction, right? Magnetic field, electric field, we just seen that. So the electric field is a vector is a vector. The magnetic field is a vector. Okay, just so you know. All right. Am I missing anything? I don't believe so. All right, so I'll stop there. Any questions?
No.
And I'll see you guys next time then, inshallah.
Okay then, Allah Hafiz.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz.